So first, let me introduce myself. My name is Morten, and I will be the host of this session. And I will start by doing some introduction, and then you're going to hear a presentation by our presenter, Vincenzo Carbone, about the TLEMsafe legacy. And his talk is titled "Towards Personalization of Musculoskeletal Models and Prediction of Functional Outcome." After his presentation, I'm just going to say a few final words about the TLEM 2.0 model in Anybody. And in the end, we're going to do a questions and answers session. But before Vincenzo has a chance to start, I just want to talk about some technicalities here. For those of you who haven't attended these kind of webcasts before, on the right-hand side of your screen, you will see a control panel. And you can expand and collapse this control panel by clicking the small red button. And inside the control panel, you can find a questions pane, as you see here. If you think of a question during the presentation, don't wait and ask it after. Just type it in here, and the staff that we have here will try to answer your questions directly, and we might also save the questions for the end, for the presenter to answer. And if your question is not addressed, we'll try to do so by email. Then let's get started. First of all, what is TLEM? What is the 20 lower extremity model? First of all, the 20 lower extremity model is the title of a PhD thesis by Martijn Klein-Horsman from 2007. It's quite an impressive work, and I encourage you to take a look. It consists of a comprehensive cadaver study and an implementation of a computational model and a lot of validation. The 20 lower extremity model is also a data set that was published in Clinical Biomechanics in 2007. This is the paper you see here on the lower part of the screen. When I checked yesterday, this paper had 199 citations, according to Google Scholar. And I think that number actually underestimates how much the data set is actually used. I see a lot of people using different implementation of this data set that don't really cite the original paper. So it's a quite influential paper, I would say. But the 20 lower extremity model is also an implementation of the leg model in the Anybody Managed Model repository. So this gives you an overview of what people talk about when they say the 20 lower extremity model. Then what is the TLEMsafe? TLEMsafe is a EU project that ran from 2010 to 2014. It was coordinated by Professor Nico van Donschot, and it was a project with 3 academic partners and 3 industrial partners. And in some ways, it was also a continuation of the big work of Martijn Klein-Horsman. But you will hear much more about this when I give the word to Vincenzo. And Vincenzo is the presenter today. Vincenzo has a Master of Science in Mathematical Modeling in Engineering from University of Turin and University of Milan. He's a PhD fellow at University of Twente, and he has been a project manager on the TLEMsafe project. He's also one of the principal researchers in the development and implementation of the new 20 lower extremity model. And he is one of the main authors of this paper on the new data set, which was recently published. And without further delay, I will give the word to Vincenzo. So Vincenzo, I'll just unmute you here, 2 seconds. So now, Vincenzo, you should be able to speak, and I will make you the presenter so you can show your screen.
Okay, thank you, Morten, for your introduction. Yeah, and good evening, everyone, or well, good morning, depending on from which country are you connecting from. So as Morten just said, this webcast will show the research work and achievements reached by the TLEMsafe project in the field of personalization of musculoskeletal models of lower extremity and the prediction of functional outcome of surgical operations. First of all, a very short introduction of the presenter. My name is Vincenzo Carbone. I am a PhD researcher at the Laboratory of Biomechanical Engineering of University of Twente, and my research focuses on the creation and validation of subject-specific musculoskeletal models. For the past 2.5 years, I've worked also as TLEMsafe project manager. I would like to mention 3 colleagues which collaborated to the TLEMsafe project and gave an important contribution to the research work that I'll show you today. From left to right, you can see Sjoerd Kolk from the Radboud University Medical Center and Pim Pelikan and René Flout that worked together with me at the University of Twente. Here is an outline of the topics that I will bring up during the webcast. I'll start introducing the objective and main achievements of TLEMsafe project and the role of each partner. Then I will show you the new TLEM 2.0 musculoskeletal dataset and how it was combined with several personalization techniques to obtain subject-specific models. I'll show you then some results about the effect of personalization on musculoskeletal model outcomes. And finally, I'll present you the techniques developed to predict the functional effects of a surgical operation, that is the patient-specific kinematics and kinetics in the post-operative situation. TLEMsafe was a project funded by the 7th Framework Program of the European Union. It consisted of 3 university and 3 industrial partners. Objective of the project was to create a patient-specific navigation system for pre-operative planning and execution of complex musculoskeletal surgery, such as joint reconstructions, prosthesis implant, or muscle tendon transfer. This system aimed to help surgeons to safely reach the optimal functional results for the patient. TLEMsafe project was coordinated by University of Twente in Enschede in the Netherlands, whose role was to develop and validate subject-specific musculoskeletal models of the lower extremity and to analyze the adaptive capacity of patients after surgery. Starting point of the project was TLEM, that is the first complete model of the lower extremity used to reproduce the musculoskeletal system of the patients in order to predict the functional effect of surgical operations. Another partner was Radboud University Medical Center in Nijmegen in the Netherlands, where all the medical surgical procedures and the lab measurements were performed. Complete functional dataset, including optical markers, force plate and EMG measurements from the gait lab, and maximal forces measurements, medical images such as MRI, CT, and PET scans were collected for healthy subjects and for hip dysplasia and sarcoma patients. Materialise company from Leuven in Belgium was responsible to process and analyze all the medical images using their software Mimics Innovation Suite, and to develop new tools to extract personalized parameters such as segmented bone surfaces, position of muscle attachment sites, and muscle volumes from MRI and CT scans. Role of Warsaw University of Technology was to create a 3-dimensional virtual reality system where surgeons could pre-plan their surgical procedures, such as osteotomy, prosthesis implant, and muscle tendon relocation, on the patient-specific model. Anybody Technology from Aalborg in Denmark provided the Anybody modeling system as the software framework for all the musculoskeletal simulations used to reproduce all the different activities tracked in the gait lab, such as walking at different speeds, sitting down and getting up from a chair, or climbing stairs. Moreover, they integrated the modeling system with the virtual reality environment in order to directly reproduce the pre-planned surgery on the patient-specific model and to simulate the functional effects. Finally, Brainlab company from Munich in Germany integrated the virtual reality environment into their surgical navigation system so that the surgeon could upload their pre-planned surgery and be assisted to exactly reproduce it in the operating room. In this slide, I briefly recap the different steps of the TLEMsafe patient workflow. Medical images and functional measurements of the patients are used to extract personalized parameters of his musculoskeletal system, such as bone surfaces, position of muscle attachment site and muscle volumes, or muscle tendon parameters, in order to create a patient-specific model. The model is then loaded into the virtual reality environment where the surgeons can pre-plan different surgical procedures and evaluate the functional effects on the patient. That means if the patient will be able to walk or getting up from a chair or climb stairs after the operation. Finally, the surgeon is able to select the optimal plan and upload it into the surgical navigation system in order to exactly reproduce the selected plan, so that the patient can reach the optimal functional results without risks of further corrective surgery. As a main achievement for TLEMsafe project, all the steps of the TLEMsafe patient workflow were successfully connected, and the data flow was validated. In fact, we were able to create a model reproducing the musculoskeletal system of a cadaver specimen and load it into the virtual reality environment, where a surgeon was able to pre-plan different surgical procedures, such as triple osteotomy on the pelvis and muscle tendon relocation, and then the surgeon was able to exactly reproduce this surgical procedure on the cadaver specimen with the assistance of the surgical navigation system. Within the TLEMsafe patient workflow, the role of University of Twente was to create and validate personalized models using MRI and functional measurements, and to quantify the adaptive capacity of the patient after surgery. For complex biomechanical applications, such as the prediction of a functional outcome of a surgical operation, an accurate description of the musculoskeletal system of the patient is necessary. For this reason, our goal was to create a model template that could be easily combined with image-based scaling techniques and morphed into personalized models. The problem was that the only MRI scan available of the cadaver specimen used for TLEM model had a very low quality, respect to our required accuracy. Hence, we needed to update the Twente lower extremity model. For these reasons, we created the Twente lower extremity model 2.0, a new complete and consistent dataset of musculoskeletal geometry based on a single cadaver specimen. TLEM 2.0 includes CT and MRI scans and segmented bone surfaces, muscle volumes, and external fat and skin layers. Now, I would like to warn you that the following two slides contain pictures and videos of cadaver experiments that may offend your sensibility, so viewer discretion is advised. In TLEM 2.0, muscle attachment sites, muscle line of action, and wrapping surfaces were measured on the cadaver specimen. Moreover, joint center position and joint axis direction were estimated from relative position of bone segments within the joint range of motion. In this video, an optical tracking system was used to calculate the position of femur with respect to tibia in order to estimate the direction of the knee joint axis. Finally, TLEM 2.0 musculoskeletal geometry was combined with muscle tendon parameters from original TLEM dataset, and the new musculoskeletal system was implemented in the Anybody modeling system and integrated with the existing model of the upper body. TLEM 2.0 was purposely built to be easily combined with the new image-based scaling techniques that were developed in TLEMsafe project, and had a central role in the modular workflow that was defined to obtain personalized models semi-automatically. Several techniques were developed to obtain subject-specific musculoskeletal geometries and muscle tendon architectures. In particular, for subject-specific musculoskeletal geometry, firstly, we segmented bone surfaces from the MRI of the subject. Then, an automatic nonlinear morphing was applied from TLEM 2.0 template to subject-specific bones, under the assumption that muscle tendon attachment sites follow the morphed surfaces, as shown in the paper published by Pim Pelikan. In these videos, you can see the morphed attachment sites on the pelvis, femur, and tibia and fibula bones after the non-linear morphing. Finally, joint geometry was estimated from bone surfaces. In particular, center of hip joint was estimated from the spheres fitting the acetabulum of the pelvis and the head of femur, while center and direction of the knee joint were estimated from the cylinder fitting the posterior condyles of the femur. For subject-specific muscle tendon architecture, we firstly applied a non-rigid registration from TLEM 2.0 template to the MRI of the subject to automatically calculate muscle volumes. Muscle volumes are really important because they are directly correlated with the maximal isometric muscle forces that are used in the model. Subsequently, functional scaling of tendons leg length and optimal muscle fiber length was performed in order to reproduce the maximal isometric and isokinetic torques measured on the subjects. In this video, you can see an example of measurements of knee isokinetic torques during maximal voluntary contractions for one of the subjects analyzed. Muscle tendon parameters were then optimized under the assumption that muscle activity necessary to reproduce the measured maximal torque is equal to 100%. The functional dataset of 10 healthy subjects were applied to the TLEMsafe modeling workflow implemented into the Anybody modeling system to easily obtain 10 subject-specific models. Subject-specific models showed large differences when compared to linearly scaled models that are scaled based on the relative position of the optical markers attached to the subjects during gait lab measurements. We found on average differences up to 12 millimeters for the segment sizes, differences up to 25 millimeters for joint center position, and up to 10 degrees for joint directions. Also, large differences between the subject-specific model and the linearly scaled model were found for muscle moment arms and muscle tendon attachment sites. In particular, differences larger than 20 millimeters were found for the muscle tendon attachment sites that are known to be the most sensitive, based on our previous sensitivity analysis. Large differences were also found in muscle tendon parameters, with some muscle tendon parts presenting differences larger than 40% for maximal isometric muscle forces, larger than 25% and up to 50% for tendons leg length, and larger than 15% for nominal muscle fiber length. All these differences showed how personalized models are necessary if we aim to reproduce exactly the musculoskeletal system of the subjects analyzed. These differences had also an effect on the model outcomes. For example, we found differences in the joint net moment predicted by the subject-specific model. And in general, we found differences between the predicted joint kinematics based on the optical markers. For example, we found large differences in the joint kinematics predicted for the ankle plantar flexion and for the subtalar eversion. Moreover, we found differences in the predicted joint net moment. That is the moment that the muscle needs to generate so that the model can reproduce the measured movements. In general, we found a slight direction of the joint net moment predicted by the subject-specific models compared to linearly scaled models. As you can see, for example, in the ankle plantar flexion or in the hip adduction joint net moment, indicated that personalized models are more efficient when reproducing a movement performed by the subjects analyzed. Finally, muscle activity predicted by the subject-specific models showed a reduction under the 100% limit, and had good correlation with the measured EMG. Unfortunately, it is difficult to validate model predictions with EMG since they are prone to measurement errors, and since EMG can be measured only on superficial muscles. An innovative technique was to validate musculoskeletal model prediction was to determine the energy consumption of the muscles of the lower extremity during walking using PET scans. A radioactive marker injected into the subjects accumulated in muscles during walking. Then, a PET scan was used to detect its concentration into the subject muscles. The results of the PET scan were then registered with the CT scans, so that we could calculate the exact amount of radioactive glucose that accumulated in each muscle. This data, presented in a paper by Schurtkolk from the Radboud University Medical Center, represent extremely valuable information to validate musculoskeletal model predictions in the future. An important aspect of the TLEMsafe modeling workflow is its adaptability to include more details, depending on the required accuracy of the problem analyzed. For example, TLEM 2.0 was successfully combined with a very detailed 11 degrees of freedom knee complex joints and was combined with the force-dependent kinematics in the Anybody modeling system. This combination allowed winning the first prize at the 5th Grand Challenge competition to predict in vivo knee loads at the World Congress of Biomechanics in Boston last year, demonstrating the validity of the TLEM 2.0 model and also the validity of the underlying modeling framework. The modeling workflow was then adapted to reproduce the musculoskeletal system of different patients. In particular, we were able to extract the asymmetric musculoskeletal geometry of hip dysplasia patients from MRI scans, and then to reproduce it during musculoskeletal simulations. We also replicated the surgical procedures performed on the patients, such as joint reconstruction and muscle cutting or relocation, in order to reproduce the post-operative situation. The modeling workflow was also adapted to reproduce the post-operative situation of sarcoma patients, where metal artifacts would affect the quality of MRI images. A collection of 6 sarcoma patient-specific models were obtained into the Anybody modeling system to be used into the next steps. The patient-specific models that I just showed you represent indeed a promising tool to assist surgeons in the pre-planning and predicting the functional effect of surgical operations. But the main question that the surgeon wants to answer is, how is the patient going to walk after surgery? In a real case, no data will be available to be used into musculoskeletal simulation. In particular, for inverse dynamic simulation, we will need to predict the patient-specific kinematics, that is the joint angles at each time step, and patient-specific kinetics, that is the ground direction forces and moments. These techniques were developed and presented by René Flaut in his doctoral thesis and will be shown here briefly. Principal component analysis was used to transform a full dataset of kinematic measurements into uncorrelated principal components, each one describing a specific feature of the walking movement. The first principal component represents the average gait pattern that was measured on all the subjects measuring the gait lab, while all the other principal components represent a specific feature that distinguishes the gait pattern of each subject from another. And we found that 5 principal components are sufficient to represent the 95% of the variability measured in the gait patterns in the gait lab. Then A linear combination of these principal components would allow creating different walking movements consistent with the patient-specific musculoskeletal geometry. The reconstructed gait patterns are characterized by, for example, longer or shorter step lengths, or using a linear combination of different principal components. The reconstructed gait would be characterized, for example, by an overextension of the knee joint in the last stage of the swing phase. Moreover, an innovative technique was implemented into the Anybody modeling system to predict the ground direction forces and moments based on Newton and Euler equations of motion. These techniques were applied to different movements, such as walking at comfortable speed, walking over an obstacle, and descending stairs, and showed very good accuracy compared to ground direction forces and moments measured with force plates. Finally, these two techniques were combined into the so-called optimal inverse dynamics, where the linear coefficients of the principal components are optimized to find the patient-specific walking pattern that minimize energy consumption. This technique showed promising results when applied to sarcoma patients to predict patient-specific gait without using any data coming from gait lab measurements. And the predictive model showed good results when compared with the normal inverse dynamics-based simulations, and also good correlation between the predicted muscle activity and the EMG measured on the patient. To conclude, today I showed you the main goals achieved by TLEMsafe project in the field of personalized medicine by connecting personalized musculoskeletal models of the lower extremity, virtual reality environment, and surgical navigation systems. In particular, the new TLEM 2.0 musculoskeletal dataset were purposely built to be combined with image-based scaling techniques in order to obtain subject-specific models in a semi-automatic way. Subject-specific models showed large improvements in the accuracy and the predictions compared to linearly scaled models. Furthermore, new techniques were developed to predict patient-specific walking movements in order to assist surgeons in predicting the effect of surgical operation. All these techniques still require further analysis and validation before their applications in clinical cases on a larger scale, but they represent a very important step to reach this ambitious goal. The TLEM 2.0 dataset, including MRI and CT scans and the segmented bone surfaces and muscle volumes, is available for non-commercial usage at the TLEMsafe project website. Also, the functional dataset of healthy subjects and hip dysplasia in the sarcoma patients, including gait lab measurements and medical images, are available for research collaborations. For this purpose, I invite you to contact the TLEMsafe project coordinator, Professor Nico Vertonskop. Finally, I would like to especially thank all the partners and colleagues involved in the TLEMsafe project in the past 4 years, whose contribution helped to reach all the achievement that I showed today. I thank you for your attention, and now I give the floor to the webcast host, Morten.
Thank you very much, Vincenzo. That was a very nice presentation. I will just make me presenter again. So, I'm just going to say a few finishing words before we take the question and answer session. So I hope everyone is able to see my screen again now. First of all, actually Vincenzo mentioned this as well. I would say that the impact of this new TLEM 2.0 dataset that has been really instrumental in the effort to win the 5th knee grant challenge at the World Congress of Biomechanics last year. In that case, they replaced the simple knee joint that is in the TLEM model with a much more advanced knee joint. And if you want to know more about this work and how it was done, I can recommend that you see these previous webcasts that we've had. One is from Valentin at Materialize, and another is from Professor Michael Skipper-Anderson at Aalborg University. These webcasts are available on our website. Also, the work on ground reaction force prediction that Vincenzo mentioned. That work was done by René together with Professor Michael Skipper Anderson, and this work has been continued. And on the 6th of October, Michael Skipper Anderson will present new advances in this work, and it will be a webcast where he both show validation on the based on some sports activities, and he will also show how you can actually apply these kind of techniques in your own models if you use the Anybody Modeling System. And then finally, I would like to say a few words about the TLEM 2.0 and when it will be available in the Anybody Modeling System, because it will be. We have a release planned here in this autumn, and the dataset will be like completely integrated so that it can be combined with any other of the body parts that are available in the Anybody Modeling System. And both versions of the TLEM model will be available. So if you use the old version, it will still be there. And the TLEM model as it's implemented in Anybody Modeling System will also support the workflow that Vincenzo has shown in this webcast. And then if you actually want access to the full data set and all the recordings, then do as Vincenzo suggested, contact Nico Fedonshot for academic collaboration.